0.007%. These are the chances for Planet 9 not to explain observations leading to its theory. But after all, what if it is something totally different? We see its impact on other objects, yet no one has observed it so far. But if humanity can reach it, it could help us make a giant leap in our knowledge by better understanding the solar system formation, explaining the history and constituents of the universe, and giving us the key to unify fundamental laws of physics. All of this because it could be a black hole. But then, where is it? Well, so far, we only know its approximate orbit and mass. Its first reference as Planet 9 was in 2016 in a study by astronomers Konstantin Batygin and Michael Brown from Caltech. They calculated its presence mathematically, which Trujillo and Shepard, other astronomers, did already since 2014. The common aspect to both these studies is that they base on a specific group of objects in the outer limits of the known solar system, the Trans Neptunian Objects. At the far edges of the solar system, farther than Neptune, there is a second asteroid belt, the Kuiper one. It is believed to host mainly dwarf planets and asteroids, of which many were discovered only recently, but also comets. However, there are certain objects scattered even farther than the Kuiper belt. They are called the extreme Trans-Neptunian objects. And these objects are what intrigued Batygin and Brown because not only do they have similar highly elliptical orbits, they also are clustered in the same region in space. Take the Sednoids, the family of objects similar to Sedna, a dwarf planet discovered in 2004. Sedna's orbit perihelion, the closest point to the Sun, and aphelion, the farthest one, are respectively 76 and more than 800 astronomical units, the distance between Earth and the Sun. Sedna's orbit cannot have been stabilized there by Neptune, since, even if it is the farthest known planet in the solar system, it orbits only at 30 astronomical units. And the traditional scenario where Jupiter would be the only responsible by ejecting them does not click either, since, again, their perihelion would be much closer. But if you add Planet 9 in the opposite side, the models suddenly work. Oh, and by the way, what you see here in this circle is the Sun and all the planets we currently know in the solar system. That should give you the perspective of the distances we are talking about today. And this is not the first time a planet's existence is calculated mathematically using other objects' behaviors. In the 19th century, astronomers used the anomalies in the orbit of Uranus to discover Neptune, and the anomalies from Neptune's orbit served as baseline to discover Pluto. So, quite normal approach, with the exception that telescopes are much more capable now than they were in the 19th. But the main difference is also the calculation capabilities. In fact, Batygin and Brown calculated that the Sednoid's configuration, at least with the currently known objects, has only 0.007% chances of happening. Alright, but what does Planet 9 has to do with the black hole? Well, since no one has seen it yet, maybe it's too far, or maybe it's something else, totally invisible. In 2020, astronomers Jacob Scholz and James Unwin wondered if Planet 9 could be something more, say, exotic. Based on its 10 Earth mass and its origin, similar to Planet 9, which could be a capture by the Sun's gravitation, their conclusion is, if Planet 9 has chances of existing, those chances would be similar for it to be a black hole. But not any black hole. A very specific one, which astronomers think they might only have observed very recently as a gravitational lens. Gravitational lensing, although not named as such back then, was first theorized by Karl Schwarzschild based on Einstein's relativity equations. Among other things like black hole event horizons, he predicted that if a mass is concentrated enough, the space-time deformation its gravity produces would deviate light. Back then, this seemed so unrealistic that even Einstein himself thought black hole singularities as not convincing and not existing in the real world. Of course, we now know very well that light is bent by even smaller masses and that black holes do exist. We detected their gravitational waves thanks to LIGO. And we took the two famous pictures of Messier 87 and the Milky Way central black hole. But what we see in these pictures are only the accretion disks of those black holes, or at least the gamma and X-rays they emit. When a black hole has no accretion disk, it is totally invisible to our telescopes. And this is the gap the gravitational lens in observations can fill. Take a very distant star or galaxy, which we would only barely see in normal conditions. If a big enough mass transits between us and this object at a specific angle, the mass bends light and gives us such pictures. This is the same object, only magnified and duplicated. So far, James Webb and Hubble telescopes gave us thousands of these pictures, and this is exactly what Schwarzschild predicted and how massive invisible objects can be detected. There is actually an experiment to catalog those objects that has been running since 1992. Its main focus is in the Milky Way and the Magellanic Clouds, small galaxies orbiting our own. You might have heard of the rogue black hole they discovered in 2022. Well, it's only one discovery out of many microlenses it observed. The majority are not even related to black holes, but 6 of them are quite special. They are very small, only few Earth masses, but their transit was way too quick, something astronomers are not sure to fully understand. See, the black holes detected via gravitational waves were stellar ones. This type of black holes are created when a star dies and its remnant neutron star exceeds 2 to 3 suns. It then collapses under its own mass. The two black holes directly imaged in the center of Messier 87 and the Milky Way galaxies are actually supermassive black holes. Most of the galaxies studied so far seem to orbit one. They are thought to become those gargantuan ogres by accruing matter. And of course, between these two categories, astronomers believe there could be an additional intermediary type. However, these 3 categories would be too large to explain the OGLE observation we talked about. Luckily, there is a 4th category that has never been detected and could explain the observation: primordial black holes. Unlike the other types which accrue mass throughout their existence, these black holes are thought to be identical to when they formed, right after the Big Bang. For that reason, they have a light mass and of course a small size. And by the way, if it is the case, if this is what the OGLE observed, then that might mean that those black holes are much more common in the universe. So much so that they might explain part of the missing mass, which is currently attributed to dark matter. In any case, Schultz and Unwin predicted that if Planet 9 was a black hole, it could be a primordial one. Its size would be the equivalent of a small melon, even though it would weigh as much as 5 to 10 Earth masses. Of course, the theory could still be proven wrong, and our black hole with it. Even if current knowledge tends to refute this possibility, Sednoid's orbits could end up being explained by the combined gravitational influence of multiple objects among the plenty still awaiting to be discovered there. But if Planet 9 theory is verified and it is indeed a black hole, studying it could be a giant leap in physics, because so far we don't really know much about what they are, except how they form. Take a dying star that will transform to a stellar black hole. What we know so far is it has fused hydrogen to helium, then helium to carbon, then neon, oxygen, silicon, and then nickel and iron. With iron, it enters its death phase actually, since iron requires more energy to fuse than it generates. Once the fusion energy is gone, the star stops fighting its gravity. The pressures are so immense that electrons fuse with protons, generating a neutron star. But after that, we know nothing. What happens to the matter after it collapses into a black hole? What becomes of this neutron core? Do neutrons transform into some quantic soup? Where do they go? The only characteristics we know of black holes are their mass, their spin, and their electric charge. Some theorize that what happens inside the singularity is matter being absorbed into space-time itself. That what happens inside black holes is between general relativity and quantum mechanics, or something else. So studying our black hole from close might help us unify all those laws explaining the universe at its smallest scales. We could send probes to it, or even an impactor, that could provide us with priceless information on its gravity and how matter reacts when reaching its event horizon. But in order to do that, we would still need to find it. So, how? Well, it depends what it is. If it is a planet, the Transiting Exoplanet Survey satellite could have already captured its signature in its large sky survey searching for exoplanets. As I'm writing this video, scientists are already analyzing its vast data library, so we might hear about it soon. Of course, some ground telescopes are already running surveys of the areas where its calculated trajectory should take it. And the new European Extremely Large Telescope, as well as the Vera Rubin one, could solve this mystery once and for all. But if we are to search for a primordial black hole, the task would be on another scale of complexity. The first difficulty is seeing a potential accretion disk that small. Given its distance from the Sun and the scarcity of matter there, it would be a 1 in a million or more chances to see it accreting any matter. Using the OGLE, we could also see its gravitational lensing effect. But here again, we would need a huge luck to have a star or a galaxy transiting behind it at the right distance and right when we observe its location. But to image it directly, the challenge is even bigger, a technological one this time. I said earlier that black holes do not emit light. Well, this was a shortcut. They actually emit a very faint light, the Hawking radiation. The Milky Way central black hole, for example, radiates at a temperature of 100 trillionth of a Kelvin. So unfortunately, to detect this radiation, we would need to reach an even lower temperature and then apply it to a totally new type of imaging spectrometers. Alright, let me ask you a question. What did you think about this format? I think this is the one I will start using in order to explain you any interesting science I can find. Let me know in the comments what you thought about it and if you have any ideas I should cover next. If you want to know more about the imaging spectrometers, I explained how they work and how they are used to fight climate change. All of it in this video. And until I see you next time, smash the like button and subscribe. My name is Khalid and I talk about interesting science.